So you collected data, you tried to fit a curve to your data. Let's now derive a theoretical model for the same situation. We think that the viewable area should be a function of the distance that you're standing from the board. And I've drawn a little sort of guide to help imagine this. If I've put my eye straight to the tube, I think that the viewport, or like the circle that I can see, should be related to like facts about the tube. So spend 10 minutes in your group and do your best to try and come up with a theoretical model. We're going to label this distance d. As I just said, I think several other measurements are probably relevant here, but I want you to be free to invent your own names and label them clearly in your diagrams. And then in 10 minutes, we'll do a quick debrief. Go ahead and pause the video because I'm going to start my debrief in like 10 seconds. Okay, let's debrief. So I've redrawn the picture here. The thing that I'm interested in finding, let's sort of break this down. So if I could find this length here, which I'll call x, that's like the diameter of the circle that I can see. I'm not sketching the circle, but it's right here. So if I could find this diameter, or if I could find the radius, then I can use the area of a circle formula to figure out the area. So that's my goal. I want to try and figure this out. I'm noticing I have a triangle here. We know a lot more facts about right triangles than we do non-right triangles, so I think it's always useful to set up the problem so that it involves shapes that you know facts about. So let's add a kind of center line here, and it should be symmetric on the top and the bottom. And now I've got two triangles. So what other facts are relevant here if I want to try and figure out, here, let's call this 2x now so that this distance can be x. So what could I figure out here that would let me know about this height x? It seems like the facts about the tube are going to be relevant to the shape of this triangle, because if I kind of zoom way in here, I can see a little tiny triangle that should be similar to this larger triangle. So I've got triangle here and I've got larger triangle here. So let's call this L the length of the tube. And let's call this capital D the diameter of the tube. So it seems like, yeah, like one way to set this up could be with trig, but I'm kind of feeling similar triangles. So remember, if you have similar triangles, let's draw a little sketch of what I've got going on here. So if you have similar triangles, side length ratios of similar triangles are the same. So like this side divided by that side should be the same as this side divided by that side. So the situation we're in is, if I'm just looking at this upper triangle, it's sort of like this scenario here. This is L. This is d over 2, this height here, because d was the entire diameter of the tube. Actually, you know what? Let's keep this simple. Let's call this r for radius, because that'll keep the algebra a little bit easier. So r is like the radius of the tube. And I was calling x way out here the radius of the viewable area. And then this was d. So if I'm going to set up some triangle ratios, I know that this side divided by that side should be the same as this side divided by that side. So in other words, r over L should be the same as x over L plus d. We've written everything here in terms of variable names, but there's really only one variable. Oh, sorry, this isn't capital D, this is lowercase d. Well, I guess there's two variables. So lowercase d is the independent variable, that's the thing we're changing, and lowercase x is the dependent variable. It's the thing that's getting affected. All these other two things, L and R, these are constants for our situation because they're facts about our tube that aren't changing. So before we use algebra, so the reason I'm telling you this is because before we use algebra, we want to think, what are we trying to isolate here? I'm trying to isolate x because that's the thing I'm solving for. So if I just multiply by the denominator, I've got L plus D, that quantity, times R over L equals x. Let's go ahead and simplify this one step to see if it takes on a simpler form. So I'm going to distribute this in here. So this will give us LR over L plus RD over L equals X. Here, L divides L. So I've got RD over L plus R, I just reordered those two terms, equals X. Okay, well, I'm not done yet because remember, I'm trying to calculate the area. And I know that area equals pi r squared, where r is my radius here. So x is my radius in the diagram. So pi x squared. So let's take this thing and square it. So now I've got area as a function of d is going to be pi times this whole thing squared, which is RD over L plus R quantity squared. Okay, cool. So what family of functions is this? Let's remember what's actually our variable here. Let's pretend like R is 1 and L is 2 for a second. You could imagine plugging this in and it'll be a lot more obvious what the family of functions is. So that would be like pi and then R is 1. So this will be d divided by 2 plus 1 squared. So if you look at that, it's like, aha, d is our variable and we're squaring it. So this must be a quadratic function, which you'd sort of expect it to be because we're trying to calculate area over here in terms of something linear. So it sort of makes sense that you would end up with a quadratic equation. Okay, so whenever you see an answer to something like this, you want to pause and ask yourself, what do I want to take away here? What were the big learnings? So I think one big learning for this particular scenario might have been, well, let's do them in order. So big learning number one was introducing this horizontal line so that our situation involves right triangles. That was a good idea. And the general learning is if you can impose a framework on your scenario that connects to mathematical facts you know, that'll probably make the problem easier to solve. So here, adding the right triangle connected to facts about right triangles. Another general thing to know is it's totally fine to add variables that describe aspects of the situation that are relevant. That's an important part of modeling. A mathematical fact that you might not have remembered was this thing about similar triangles. It's a sort of a mundane fact. It's going to be really useful for solving a lot of calculus problems next year, so it's a good thing to kind of remind yourself of. And then the last thing is just being comfortable with the algebra and getting comfortable doing algebra where there's a lot of variables and keeping track of which of the variables are actually constants and which of the variables are actually variables. You have to decide where you're trying to get to. Okay, I want x to be by itself, and on the other side I want d, and then being able to interpret your results. Okay, let's try and set up another one.